Hello and welcome to our first video for the chapter 3, part 1 chapter. And we're going to be actually starting with one section from chapter 2 because it fits better in here. And we're going to be looking at something called a derivative for the next few chapters. So this chapter is learning how to calculate them. And then next chapter, we will learn how to actually use them to solve problems. So, when we're talking about calculus, a lot of the time we are talking about how one quantity changes in relation to another quantity. So, what I mean by that is, for example, let's say you have a ladder leaning against a wall. If that ladder starts to slide down the wall, the bottom of the ladder must at the same time slide away from the wall. And how fast it falls down the wall will directly affect how fast it moves away from the wall at the same time. But in order to solve problems like that, we need to be able to do the mechanics of the math first. So in our previous chapter, chapter 2, we talked about finding the slope of a tangent line, and we had a special equation for that. We actually had two of them, but there was one that I said was my preferred one, and it's because it's going to come up again today. We used that same equation to find instantaneous velocity. So, just a reminder, a tangent line was a line that touched a curve at exactly one point. But in order to find the slope of a line, we usually need 2 points. And so, if we thought of the point on the tangent line, if we thought of another point approaching that point and getting very, very close to our point of tangency, infinitely close to our point of tangency, we could find the slope of that line. So, also a reminder from Math 10 that a slope of a line is simply a rate of change. So, if you find the slope of a line, really what you're doing is you're finding the change in y over the change in x. So, how fast is y changing with relation to x? So, this notion of slopes and rates of change and the rate of change at a specific value is so important that they named it its own thing called a derivative. So, what a derivative is just the slope of a tangent line. And we can use the same limit formula we used to find the slope of a tangent line to find our derivative. So the notation you see here is one of the more common notations you will see. This notation, F with the little apostrophe of X, means derivative. Okay, so we read this as F prime of X. Okay, so f prime of x means we have found the derivative of the function f with respect to the variable x. Okay, you can only find the derivative if the limit exists. If the limit doesn't exist, that means that the derivative does not exist. If you can find the limit or find the derivative, we say that f is differentiable. So if a question says, is this differentiable? What they're really asking is, does this limit in the red box exist? Okay. There are some other notations. Y prime, you will see a lot this chapter. F prime, you will see a lot this chapter. Dy dx, you might see this chapter. You will for sure see it next chapter. We deal with this one almost exclusively next chapter. Okay. The rest of them you won't see as much, except this guy here. Okay. And you'll see that I've got this down on the next note section. And this is because d dx tells us we need to find the derivative. So this is like an instruction telling me find the derivative of f. Okay. If I have y prime, f prime, or dy dx, that means this is the derivative. So dy dx, y prime or f prime is our derivative. D dx tells me I need to find my derivative. It's like an instruction. Okay. So again, f prime of x is simply the slope of the tangent line. That's all this is. Okay. So if I am asked to find f prime, really what I am being asked to find is the slope of the tangent line. Okay. And it says use the definition of the derivative. Well, the definition is that f prime, or your slope of your tangent line, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Sometimes they will actually give you an x value, which we will see later on. Okay, so if I want to find this, this is going to be the limit as h approaches 0. F of x plus h would be 5 of x plus h squared minus 4 minus f of x. F of x is 5x squared minus 4 all over h. Okay. Now, if I expand this, I get the limit as h approaches 0 of 5 x squared plus 2xh plus h squared minus 4. If I expand the first brackets, if I expand the second brackets, then I can see that I can cancel out my 2 4s. Now, you may also notice here that your x squareds are going to cancel out, but you might not. If not, we would keep going. We're going to expand the first brackets again. And now we can see that our x squared terms will cancel out. So this is the exact same math we were doing in the previous chapter. We're just calling it something different. We're calling it a derivative instead of calling it the slope of the tangent line. Okay. And we can see that the h from the bottom can cancel out with an h in each term from the top. And once we are all simplified, we can actually evaluate our limit. If I plug h as 0 in, I just get 10x. The 5h term becomes 0. Okay. And we can repeat with b. I've got the limit as h approaches 0, f of x plus h minus f of x all over h. You don't need to write that out every time you do a question. I'm just doing it here because we can't see it on my screen at the same time. So f of x plus h is going to be 3 times x plus h minus 2. F of x is 3x minus 2 all over h. I need to expand my brackets, and I get 3x plus 3h minus 2 minus 3x plus 2. And you'll see we've got a bunch of stuff that cancels out. Our 2's will cancel out, and our 3x's will cancel out. This leaves us with 3h over h. Those h's will cancel out, which means I have the limit as h approaches 0 of 3, which is just 3. Now, I showed every possible step for both of these questions. You might have seen, for example, the blue one, example 1a. You might have canceled out the 4's and the 5x squareds all in one step. Okay. So this is like every possible step you would use for these questions. Okay. Now, something we're going to take a look at is what slopes of tangent lines look like on a graph. And Also, eventually, we're going to be looking at what a graph of a tangent would look like and how that compares. And so we're going to be seeing quite a few relationships between uh, f and its derivative. So f and f prime, we're going to be seeing a lot of connections throughout this chapter as to how they relate to each other. And we're going to be learning some shortcuts later, the chapter as well. But for today and the next set of notes, it is a little bit tedious, just as a heads up. Okay. So this one is asking us to arrange these four f prime values from least to greatest. We have a curve here that is our f. So remember, f prime of -7 means if I go over to -7 and I draw a tangent line, what is my slope? Well, I don't need to know exactly, but I know that my slope is positive. Okay. If I go over to -5, if I had a point there and I drew myself a tangent line, my slope here would be 0, my slope of that line. If I go over to 0, draw a point, draw a line that looks like it kind of touches that point and only that point as best we can, this one has a slope that is negative. And if I go over to 8, draw a point, draw what looks like a tangent line, we see that this one has a slope that is positive as well. So if I want to arrange these from least to greatest, well, my least must be my negative slope, or f prime of 0, then my 0 slope, f prime -5, and then my two positive slopes. So just a reminder, a bigger slope means a steeper line, which means that the purple slope, or f prime of 8, is bigger than f prime of -7. So f prime of -7 would come next, followed by f prime of 8. Okay, and that's because this one's -0, these two are positive, but -7, the line there would have a smaller slope than at 8. Okay. The next one, instead, they're actually giving us the values and they're asking us to draw a line that would work. Notice how it says a function, and that's because there are many that would work. We're just going to sketch something that could work. So I'm going to start with this point here. This is f of 0 equals 0. Okay. Now I also know I'm given some information when x is 1 and when x is 2. So I'm going to put a 1 and a 2 on my axis. Okay. It's telling me that at 0, an x value of 0, the slope of my tangent is 1. That's what that says. Okay. So I know that my slope of my tangent here is 1. Okay. That's my tangent line. Okay. I also know at 2, my slope of my tangent is -1. Okay. So this is also a tangent line. So now if I think about this logically, what it looks like is that the graph, as I read the graph from left to right, it looks like it must go up and then come back down, which makes sense if I take a look at the last f prime that was given to me here. It says that f prime of 1 is 0. Well, if I take a look at example 2, I saw that if I had a slope of 0, that was where I had a peak or a maximum. The same thing would happen with a minimum, but that doesn't make sense for what we're trying to draw. If we were drawing a minimum, my outer tangent lines would point me downwards. So what this means is that I must go through the point 0, 0. I have to at some point come up to some sort of maximum when x is 1, and then I must come back down with a negative tangent line. Okay, this is a possible function. Okay, and we see that if we did that, we would have a slope of 0 at x is 1. Okay, we could have gone up way higher and down. That would have worked as well. Okay, this is a possible function. Okay. All right, we're going to try another definition of a derivative question that is a little bit trickier, that's going to review some of our other skills we have from chapter 2. So we know that f prime is equal to the limit as h approaches 0 of f of x plus h. For us, that would be root x plus h minus f of x, which is root x, all over h. Now, just a refresher, if you have radicals and you can't just plug 0 in here, we would need to multiply by the conjugate. Our conjugate is the square root of x plus h plus the square root of x. And we have to multiply both the top and the bottom by these values so that we're not changing our value of our limit. So then if I expand the top out, I get x plus h minus x. On the bottom, do not expand that out. It's going to make it worse. Just leave it as h times the conjugate. Then on the top, we can see we end up with x minus x. So on the top, we just have an h. On the bottom, we have h times the conjugate, which means our h's cancel out. And we are left with the limit as h approaches 0 of 1 over the conjugate. Now I can plug my h is 0 in and actually evaluate the limit, and I get 1 over root x plus root x, or 1 over 2 root x. Okay. Now, the next part is saying determine the slope of the tangent line. Well, all the slope of the tangent line is f prime. That's all that is. We already found f prime, and it's giving us an x value. So if I want to find f prime at 16, I'm being asked to find f prime of x when x is 16. This means I'd be finding f prime of 16. So I can plug 16 into my f prime, which gives me 1 over 2 times 4, or 1 over 8. Okay. Now, if we want to determine the equation of the tangent line, remember this is y equals mx plus b. We have an x, we have a y, we have an m. Our m is our slope of our tangent line when x is 16. So m is the 1 over 8. We need to find b. So we have y is 4. Our m we just found was 1 over 8. Our x is 16, and we need to find b. So we get 4 equals 2 plus b, or b equals 2. So we have y equals 1 over 8x plus 2. Okay. Again, the math we just did in example 4 here is no different than the math that we did before the break. We are just calling it something different. Okay, we determine the slope of the tangent line, which is f prime. We then use that f prime or slope to find the equation. The math itself is the same. Okay, we're going to do one more where we look at our position. So just a reminder, velocity. When t is 2, this would be instantaneous velocity. V of t is equal to the limit as h approaches 0, f of t plus h minus f of t all over h. And v of t is the same as f prime. Notice, this limit is the same as our f prime. Okay, so if we find this, our velocity is the limit as h approaches 0 of f of t plus h. So this is 1 over 1 plus t plus h minus f of t, 1 over 1 plus t. And this is all over h. Now it told me when t is 2. So you have a choice. You can plug t is 2 in here if you think that would help you, or you can do this all algebraically and wait till the end. Okay. I'm going to plug t is 2 in now. If you look at the examples posted online, the PDF answers, I've shown the algebraic method where we don't plug 2 in until the end. So if you want to see the other way, take a look at the PDF. So if I want to find v of 2, this is going to be the limit as h is 0, 1 over 1 plus 2 plus h minus 1 over 1 plus 2. I'm going to rewrite this instead of divided by h. I'm going to write this as 1 over h. Okay, and I've plugged a 2 in. Okay, now I can fix this up a bit. This becomes 1 over 3 plus h minus 1 over 3 times 1 over h. In the square brackets, I need to make a common denominator. So my common denominator would be 3 times 3 plus h. So this becomes 3 over 3 times 3 plus h minus 3 plus h over 3 times 3 plus h, all times 1 over h. So if I do this, I get 3 minus h if I expand the brackets. And I can write this as one giant fraction. My 3's on the top will cancel out. And then I end up with the limit as h goes to 0 of negative h all over 3 times 3 plus h times 1 over h. And then you'll see the h from the top and the h that was originally on the bottom the whole time cancel out. And we end up with the limit as h approaches 0, negative 1 all over 3 times 3 plus h. And remember, this is our velocity at time 2. I can then plug h's 0 in and get negative 1 over 3 times 3, which gives us negative 1 over 9 meters per second. So if we did not want to plug our 2 in at the beginning, from this step up here with the v of t, we would have still made common denominators, but we would have ended up with an expression for v of t, and we would have plugged our 2 into that at the end. If you want to see the algebraic method, it's posted online. The advantage to the algebraic method is if a question says, say, find the velocity when t is 2, and then maybe when t is 10, and then maybe when t is 25, an expression would be a lot more helpful because we could just keep plugging t in. If we do it the way we've done it here in the video, we would have to repeat this entire process for each of the t values given. So if you're only given one t value, this works. If you see your question, you've been given multiple t values, I would do the algebraic way because it will be less work in the long run. Okay. Again, there are practice questions on the bottom of the page. There are way more here than you would need to do. So pick some and try some, especially if you found chapter two a bit hard or you're feeling like this is not that fresh in your mind. Then please try a couple extra questions. But if you went and reviewed chapter two before we started this new chapter here, then you probably won't need to do as much practice today.